Hi friends, welcome to my channel. Let's have a look at problem 2415, reverse odd levels of binary tree. In this video, we are going to share two formats of solutions. So the first format is based on level order traversal and repointing, and the second one is a recursion solution. First, let's look at the statement of the problem, and then we will give a simple analysis, and finally we share the codes. So the problem statement is the following. So given the root of a perfect binary tree, reverse the node values at each odd level of the tree. So we are required to return the root of the reversed tree. So here it points out a binary tree is perfect if all parent nodes have two children and all leaf nodes are on the same level. So the level of a node is the number of edges along the path between it and the root node. So for example, in example 1, so 2 is at level 0, and this 3 and 5 marked red and blue are at level 1, and the leaves are at level 2. So in the example 1, so 3 and 5 are reversed, so we get 5, 3 here, but the second level does not reverse. So in example 2, so the root 7 has two subtrees or children, so 13 and 11. So after reversal, so the left subtree is 11 and the right subtree is 13. So similarly, you can interpret example 3. So before we look at the methods or formats, let's look at the additional assumptions or constraints. First, the number of nodes in the tree is in the range 1 to 2 to the power 14. So actually you can estimate this number. So because 2 to the power 14 is nothing but 2 to the power 10 times 2 to the power 4. So that is 1024 times 16. So the node value is in the range between 0 and 10 to the power 5. And the root is a perfect binary tree as defined here. So with that said, we are ready to look at the analysis and our plan. So here in this video, we are going to present two formats of solutions. So let's go over the two one by one. So the first one is based on level order traversal and repointing. So for this solution format, so we do level order traversal, which is very routine. So we just need to check the odd or even of the level index. If the level index is odd, we reverse that level. So for the repointing, so one needs to know the repointing we are indexing. For example, in this example 1, so at a level I, so when I equals 1, so we have 5 and 3 after reversal, right? So corresponding to this tree in the result. And the next level corresponding to level index 2, so we have 8, 13, 12, and 34. So notice that the general rule is the following. So if we have node ig, so its left child shall be in the next level, that is I plus 1, then let's regard this as column or second indexing is 2 times g, and the right child will be at next level, that is I plus 1, and the second indexing will be 2 times g plus 1. So for example, here the node 5, its indexing will be at level 1 and the first one, so that is 1, 0. Its left child is 8, right? So 8 at next level, that's level 2, and then it's the first one, so 2 times 0, right? So we have 2, 0. And the right child is node 13, so it's at level 2, so 1 I plus 1. Then the second index will be 2 times g plus 1, so that is 2, 1. So you can do a general verification. So this is the first method. So this method actually is very verbose, and the key point is that we know how to do level order traversal and how to do the repointing. So the second method or solution format is based on recursion. So this is actually very natural due to the fact that binary tree, or here perfect binary tree, is a recursive abstract data type. So for two nodes, node 1 and node 2, from left to right at an odd index level, so we try to switch the values of node 1 left and node 2 right. This is the one consideration. Another one is we try to switch those of node 1 the right subtree and node 2 the left subtree recursively. Note that at the very beginning, so node 1 and node 2 are both the root. So for this format, actually the code speaks itself. So you can check the code for the logic and the procedure, and then come back to the analysis for a better understanding. So before we write code, here are some comments. First, you can check the tree-related problem playlist in the channel. So here, actually, if we know how to implement varieties of tree traversal algorithms, then adding extra logics in between is sort of routine. So here, the extra logic is reverse the odd indexed levels. So with that said, so we are ready to look at the code. So as we mentioned, we're going to share two solutions. So the first solution is based on level order traversal. So level order traversal and repointing. So for this, I'm going to inherit the previous videos, so in which we explain how to do level order traversal using list comprehension. So here I'm going to make a list to hold the array corresponding to different levels of nodes. And then we're going to initialize an array called level, so originally the root itself. And then also we're going to initialize a variable called level index. So we're going to check odd or even of a level index. And then we just do the standard level order traversal, while level. So what we are going to do is that we check if level index is odd or even. So if it's odd, so we just append this level of nodes to the nodes. So nodes append level. So we do not do reverse. Otherwise, what we're going to do is we append the level, but with its reverse operation, right? So this is actually the way we do level order traversal. So for the even indexed level, we just use the original order. For the odd indexed level, we use a reverse order. So once this done, so we are going to update the level array or list. So we're going to use list comprehension. So for children, for node in level. So this for node in level, this is the traversal of the level from left to right. And then for child in node left, node right, if child. So notice that the order here is important. So with that done, so we are going to update the level index by 1. So this is actually routine. So once this is done, so we can do the repointing. So this first, so let's see, this first step we can make it. So this is level order traversal, but with some extra logic from this problem. And then the next part is repointing, right? So for the repointing, we just need to follow the problem requirement. So for this, so we're going to use two for loops. So for I in range, the length of nodes, so -1. Actually, we do not need the last level. Then for j in range length of nodes I for this level. So what we are going to do is that we're going to nodes ij. So its left will be nodes I plus 1, then 2 times j. Right. according to our above analysis, and then its right is going to be nodes, so next level and 2 times g plus 1, right? So notice that in the level order traversal we have done the reversal. So this is all the operations needed. So next we just need to return nodes 0, 0, right, the root. So that's a full format of solution corresponding to level order traversal and repointing. So let's do a special case check first. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So with this format of solution done, let's look at the second one. So the second one is based on recursion. So let me first mark this as V1. So actually the purpose for the first version of solution are twofold. Actually first we want to practice level order traversal, and secondly, so we want to understand the details for this problem. So with these details understood from first version, so we can write a recursion solution. So for this, so let me first make some annotation. So we're going to use recursion. So first I'm going to write a hyperfunction. So let's see, hyperfunction. So it's going to be our worker, so which does the actual job. I will call it worker. So we are going to accept two nodes, node 1, node 2, and its level. So then, so if node 1, so if not node 1 and not node 2, or if node 1 is null and node 2 is null. So then what we're going to do is just a stop or return. So this is the one case. The other cases, so we are going to check level and then write the problem logic inside. So if level is odd, so what we're going to do is that we're going to switch the values. So node 1 value and node 2 value. So we're going to switch to node 2 value and node 1 value. So this is the switch. So afterwards, what we are going to do is that, so we're going to do this thing recursively. So we're going to call this worker, and then we're going to node 1, so move to the left, and node 2, move to the right, and the level is incremented by 1. So similarly, we can do worker node 1 to the right, and then the node 2 will to the left, and then we're going to increment the level by 1. So these two lines of works are done in parallel. So then afterwards, so we get all the things done. So this is the hyperfunction. So next we're going to do function call and return. So we're going to call this function, and we're going to find root left, root right, and then we are going to check if we switch or not. So at the very beginning, actually, we can make node 1 and node 2 to be the root, and then if we start from the odd level, so that is level 1, so we can write root left and root right and level 1. So once we call this function, actually the function will do all these operations needed. So after this function call, we're going to return the root. So this is a second format of solution. So it's actually relatively shorter than first version, but the first version provides the finer details. So with that said, let's first do a special case check. Yeah, it passes the special case. So now let's do a generic case check. Yeah, it passes all the test cases. So I guess that's about the solutions to the specific problem. So before we end the video, let's give a quick summary. So in this video, we provide two solution formats for this problem. So one is based on level order traversal and repointing, and the other is based on recursion. So the first one, the main point or ingredient is that we know how to do level order traversal and do repointing. And for the second one, so basically if we understand or we can write a solution using version 1, so the second version is sort of standard. So with that said, I guess that's about it for this video. Thank you very much.